G'day viewers. In this segment we'll use a program called Traceroute to peek inside the network and see some of its internal structure. So this picture gives us the context for where we were before. You can see that using the Network Service API, sockets is what we looked at, applications talk to each other across the network. Now the Network Service API hides all of the details here of what's inside the network. So we can't really see by using it what's inside the network, how many routers we go through, what ISPs, whether it's a short path, a long path, all of this sort of stuff. Now this is actually good because we don't want you, when you're writing an application, to have to know all of those details or write programs that depend on any of those details. The higher level of abstraction is useful for us, but you might be curious to know what's actually going on inside the network. So in this segment, we're going to use a program called Traceroute, which will let us peek inside the network. Traceroute is a very widely used command tool. It's maybe the #1 go-to tool of sysadmins to sort of debug the network and find out what's going on inside it. It runs on virtually all operating systems. You can see it's often called Traceroute on Linux or Unix systems. And on Windows, it's Traceroute with a RT at the end there. Traceroute was developed by someone called Van Jacobson. We'll hear about him a little more, especially when we get to TCP congestion control. He was one of the pioneers of computer networking as the internet grew up. And the Traceroute tool we're going to look at, it works by using the network-to-network interface, I'll call it, really the IP protocol, the internet protocol, which describes how different hosts and routers talk to one another. It uses this program in sneaky ways that we'll get to later. For right now, for the purpose of this segment, you don't really need to understand how Traceroute works. It's really just a program that will run and reveal a little bit of information about what's inside the network. Okay, so here's how Traceroute works. Traceroute probes successive hops in order to find the network path between a host that's doing the probing, that's over here on the left, and a destination host that's on the right-hand side. So this might be some remote web server, and you want to find the path, the network path, between your computer and the remote web server. What Traceroute does is it sends a packet towards that remote host, only a single hop into the network, and then causes the network to send a message back, a reply back. Then it sends a packet 2 hops into the network and elicits a response from there. Then 3 and elicits a response from there, and so on. And eventually it sends it almost all of the way, elicits a response, and finally on the last time the packet will reach the remote host, which will then send a response, and we'll know that it's arrived at the remote host. All of these responses in the middle, as we get a response from routers in the middle of the network, this gives us information about what those routers are, the number of them, and the sequence in which they're organized, until over here eventually we get a packet back from the remote host, and we know that we've seen the whole path through the network. So that's roughly how Traceroute works. Here's a picture where I've just cleaned up some of those. I've cleaned up some of that figure. And as I say, we'll go into more of the details about how Traceroute uses IP to do this later on, but for now just suspend disbelief and imagine you have this tool that you can run. So let's see how it works. I'm actually in Barcelona right now, so let's try and find out what path is used in the network as I send packets from here to the web server at the University of Washington. Let's enter a command and we'll enter a traceroute. Traceroute to www.uw.edu and see what happens. I'll hit return, and Traceroute is away. What it's doing is it's sending its packets to probe successive hops. You can see the very leftmost number is the hop number. It actually sends out 3 entries for every hop. And the first numbers are the timing. So you can see initially it was very fast, within a millisecond within my house. But as we got further away from my house and further out into the network, the times got larger, up to a couple of 100 milliseconds. Now on the right-hand side, you can see the names or identifications of all of the routers. Both the IP addresses are given, as well as some of the names there. And we can take some hints from the names and work out somewhat about where the packet is going. Some of those names have Telefonica in it, so it looks like it goes through the Telefonica network, and it looks like it goes through the level 3 network. You can see San Jose there, as well as Seattle later on, and eventually it arrives in some computers at Washington. On hop number 17, we see stars back. the network actually wouldn't return any information for what was at hop 17. Something must have been there, but whatever it wasn't telling us because it's not required to implement Traceroute. Okay, so now in this slide I've taken the same information as from our example before and just laid it out a little differently to try and show you the path between my computer and the destination that I was probing. Here I call it www.uw.edu, even though in the traceroute at the end we actually saw that the name of this that name was an alias for this other computer's name, www.1.cac.washington.edu. Now I'll point out here that the ISP names and places in the middle are just educated guesses based on the information returned from Traceroute. It gives the IP address and a translation into a host name from which we're making guesses about the ISPs. So we could see that after one hop we were still inside the home network here. We came back and this was quick. For the first 3 hops or so we're inside some network called TDE. Not sure exactly what that is, you could Google it. I think that's some internal Telefonica network. Actually, I'm guessing the end of that was probably we're still in Barcelona from the BCN here. That stage, it looks like we went through a network, the Telefonica network, for 4 hops. It looks like we entered it, or shortly after we entered it, we went to New York City, and the round trip time here had gone up to about 100 milliseconds. That's maybe consistent with Barcelona to New York City. We're no longer just in Barcelona, we've gone further afield. But after 4 hops or so, it looks like we emerge in another network, this time called level 3. Sorry, they're level 3. And it looks like we enter that network in San Jose and then go through the level 3 network for 6 hops. By this time, the round trip time is rising. You can see here, I think it rose to about 180 milliseconds. This is just an estimate once again, as we went from New York all the way through the network to San Jose. So now we're on the west coast of America. We're getting close to Seattle, but we took 6 hops through level 3. And at that stage, we arrived somewhere in Seattle, and we actually went through a network called the P&W Gigapop. You wouldn't necessarily know what this is. Again, you could maybe Google it. I happen to know that's the Pacific Northwest Gigapop, which is an exchange where different networks come together in Seattle. And this network then routed us onto the UW network. By now, by the way, the round trip time's gone up beyond 200 milliseconds. And within 3 hops within UW, we arrived at the final destination. So you can see that Traceroute gives us a lot of information here. Really, they're hints. They're not always unambiguous. But Traceroute's giving us a lot of information about the paths that your packets take through the network. So you can try this yourself and find out the paths to some destinations throughout the network.